Let me start off with something that I didn't make clear enough last time. And so I'll start off by saying, let's look again at what does differentiable mean. What does differentiable mean? Okay. So remember, we said that it means that f of t equals, so differentiable at a point x. We said, well, it means that your function is basically the tangent line plus some error. Your function is the tangent line plus some error, where this error goes to 0 as x as t approaches x. That's what differentiable means. Okay. Okay. So if you were sort of I don't know, like stubborn, you might say, well, look, what about this? What about this thing? Isn't this thing differentiable at this point? Because look, I've got this tangent line here, and as I go closer and closer to x, the error between the tangent line and the function goes to 0, right? So doesn't that mean that this is differentiable? Okay. Okay. So what would capture this sort of behavior? Well, if I said this, if my definition were this, then that's what differentiable would mean, right? It would mean that your function differs from the tangent line by some error that goes to 0. Okay? So if my definition were this, then you could rightfully say, oh, then this guy would be differentiable at that point. Okay? But we have this thing here, and let's think about how that changes the situation. Okay. Okay. So so for simplicity, so this is related to what I was trying to say last time about Fermat's theorem. Okay. So for simplicity, let's say that f prime x is greater than 0. Okay. Suppose that the derivative is greater than 0. So I'm going to start from here, and I'm just going to, let me call this thing, no, I'm just going to leave it as is. Yeah, let me leave it as is. So I'm going to move the tangent line, the linearization to the other side. So minus f of x plus f prime x t minus x, right? And that's going to be equal to u of t times t minus x. Okay. So since, yeah, actually I'm going to read like this. So I'm going to take absolute values of everything. Okay. Okay. So since the limit of u of t is 0, as t goes to x, we know there exists some neighborhood of some punctured neighborhood of x in which the absolute value of u of t is smaller than f prime of x over 2. So I'm going to try and fix up something that I was doing yesterday. Okay. Right. Okay. So so think for t bigger than x. Let me rewrite this thing. Okay. For t bigger than x, we know that sorry. let me not say that first. So, right, so we have this, that f of t, so f of t minus f of x plus f prime x t minus x is less than or equal to f prime x over 2 times absolute value t minus x. Right? I'm just in for t in that neighborhood. Right? Right? Because we know that u of t, I'm just switching off the u of t. Right? U of t is smaller than this f prime x over 2, so I'm replacing it by f prime x over 2 and changes to less than or equal to. Okay. Okay. So just to make it simple, let's say that that t is bigger than x, right? That we're on the right side of that neighborhood. Okay. So here is x. There's some delta neighborhood. There's some delta neighborhood here, and we have a tangent line with a positive slope here, right? Slope f prime x, which is greater than 0. Okay. Okay. So for t bigger than x, what do we get? We get that f of t minus the linearization f of x plus f prime x t minus x is less than this thing, t minus x, and bigger than negative that thing, right? Right? Because this thing is controlled by this thing here. Right? The absolute value of this is smaller than this. That means that this thing lies between that and negative that. Right? It's smaller than, the absolute value of something is smaller than a, that means it's trapped between negative a and a. Right? You're nodding, but I'm not feeling convinced. Right? If the absolute value of something is smaller than, whoops, if the absolute value of something is smaller than a, that means that x lies between negative a and a. Right? That's all I'm using here. Right? This thing is smaller than this thing, right? So this thing is trapped between this and negative that. Yes, Susan?
Does it matter if it's less than or strictly less than?
Okay. So what does that tell me? That tells me that f of t is trapped between, so I'm just going to add this guy throughout. Okay? I add the tangent, the linearization throughout, and you see what happens, right? I'm going to get f of x plus 3 halves f prime x t minus x, right? And I'm sorry, 1/2 f prime x t minus x. And on the other side, I'm going to get f of x plus 3 halves f prime x t minus x. Okay, so what does that tell me? Right? Here's my x. Here's my, let's pretend this is my function, and that this is my tangent line. Okay. It says that if you're differentiable, right? If you're differentiable at this point, then there's some little neighborhood, x plus x, x plus delta, x minus delta. There's some little neighborhood such that your function is trapped. So this is right for t in function neighborhood, right? That your function is trapped between 2 lines, right? Your function is trapped between 2 lines, one of which has 1/2 of the slope of your tangent line, and one of which has 3/2 of the slope of your tangent line. Okay. Okay, so I only did it for the right-hand side. I leave it as an exercise to do it for the left-hand side. It's exactly the same thing, right? Right? It's just that this guy will be the lower guy, and this guy will be the upper guy, right? Okay. Okay. Right. So what is differentiable? So this shows you, right? So further, this 2, this f prime x over 2, this 2 could be whatever I want it to be, right? It doesn't have to be 2. It could be 2 billion, right? 10 to the 10th, right? In other words, I can trap this guy. I can find a neighborhood in which my function. So here's my tangent line. I can take these this perturbation to be as tiny as I like, right? I can perturb the slope by as little as I desire, right? So I can perturb it by by some tiny thing, and I know that there's going to be some neighborhood in which my function is trapped between those two bars, right? Right. So it's not. If I had something like this, well, that's never going to work, right? Because what's your tangent line? Can you trap it between these two guys? No, right? So not differentiable. Okay. So differentiable is something very, very sophisticated, right? It says that your error goes to 0, but more than that, right? It very much goes to 0, right? That no matter what lines you choose above and below your line, right? No matter how you perturb the slope a little bit above and a little bit down, there's some place where your function actually lies between those two bars, right? It's trapped between those two bars. Okay. And so this is what we could say, if we wanted to be crazy and give a proof of Fermat's theorem in this way. We'd say, well, look, if f prime is greater than 0, right? Then I know that my function is I can trap it between two things like this, and so my function has to be increasing, right? So my function has to be increasing. Okay. So yeah. Okay. We'll also use this in a proof that we're going to do shortly. Does this make sense? Okay. So this is what differentiability means. This is a deeper way of understanding what differentiability means. Yes?
So we can't trap a point between two lines.
We're going to trap the graph of the function, right? So you've got your function here, and you've got your tangent line, and differentiability means that if I take any plus and minus on the slopes, then I can find a neighborhood in which my function is between those two functions, between the upper guy and the lower guy, the upper guy and the lower guy.
And so we can choose anything above greater than 2, right?
This just means that we can perturb the slope by as little as we desire.
Yeah.
Yeah, so this is just another way of thinking about differentiation. The more math you know, the more ways you can think about differentiation, I guess. It's a notion in many fields. There's an article by the mathematician Thurston, who is a fields medalist. And he's talking about the flexibility that you need to be a mathematician. And he said, one day I decided to write down all my different ways of thinking about the derivative. And he said, here are a couple of examples, like number 34, and blah, 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 and number 35. So yeah. Okay. Okay. So, okay. So remember, we finished up last time with this thing called the Generalized Mean Value Theorem of Cauchy. It's usually it's sometimes called Cauchy's mean value theorem, right? That if you have functions continuous on AB and differentiable on the interior, then you're guaranteed a place where f prime of C times the difference g of B minus g of A equals g prime of C times f of B minus f of A. So this is Cauchy's mean value theorem. It immediately has a corollary, which we could have gotten in some other way. The standard mean value theorem, right, that given any function, continuous on AB, differentiable on the interior, there exists a point where f prime equals f of b minus f of a over b minus a. Right. So this one you saw when you were younger, right? That you're guaranteed a place where the instantaneous slope equals the average slope. Right? You're guaranteed a place where the instantaneous, given any function, as long as it satisfies certain conditions, there's guaranteed a place where the instantaneous slope equals the average slope. Okay. And the proof is, what's the proof? By the generalized mean value theorem.
And we take a g as the identity.
Take g as the identity function. Let g be the identity function. Use generalized mean value theorem. Right. Although we could have proved it before, you don't need to use it. We could have proved it before when we were doing Rolle's theorem. You can prove it directly from Rolle's theorem if you feel like it. Okay. And the mean value theorem has corollaries. If f is differentiable in AB, if f prime is greater than or equal to 0 for all x, then f is monotonically increasing. If it's less than 0, you have monotonically decreasing, and if it's equal to 0, then f is constant. Just to make sure you know what's going on, take 1 minute and prove any one of these that you feel like. Okay, turn to somebody nearby and talk with them, please.
the function itself will be increasing because you do math, pushing back the math. Because that's what's going to be is f(x) is increasing. So that's yeah, like I
Okay. So how do you prove it?
it's positive.
Which one should we do? It doesn't matter, they're all the same thing. Constant? Sure. Constant. So suppose f prime is always equal to 0, right? So it's constantly equal to. Suppose f prime is constantly equal to 0 in A, B, right? Then pick any two values. I'm sorry, pick any two x1 and x2 in the interval. Pick any two guys in the interval, right? So, so by the mean value theorem, who wants to say it? Somebody want to finish it off? Who would like to? Should I just choose somebody? By the mean value theorem, right? You know that there's some place in the middle where the instantaneous velocity equals the average velocity over the whole time interval. But you know that the instantaneous velocity is 0 everywhere, right? So that tells you that over any time interval, the average velocity is 0, right? In other words, it's flat, right? By mean value theorem, we know there exists a point between x1 and x2. Let's assume that x1 is less than x2. There's a point between these guys where f prime of c equals the average change over that time period, right? But we know that this is 0, right? But f prime c is 0, right? Because we assume that f prime is 0 everywhere, right? So that tells you that f of x2 minus f of x1 has to be 0 also. Right? So no matter what 2 points you choose, the function has the same values there, right? And so your function must be constant, right? Because no matter what 2 values, right? If I choose this guy, it's going to be the same as that guy. You choose this guy. Any 2 points I choose. If I choose any other point, it'll have the same value as at x1. And you see what we do to show monotonically increasing, right? We just go like this. Okay, let's go on. Let's go on. Okay, so there's sort of like a hodgepodge of results after this. So the first one is called the continuity of the derivative. Continuity of the derivative. So the point is this, that derivatives need not be continuous. Derivatives need not be continuous. So if you look at the function f of x equals x squared sine 1 over x for x not equal to 0, and 0 for x equals 0. If you look at this function, right, it is the sine 1 over x function, right? Sine 1 over x, as you get closer, it looks like the sine function, but you start compressing it faster and faster. It goes crazy here, right? You take that sine 1 over x, whoops, what am I doing? Sine 1 over x function, and it looks something like this, right? And then comes out like that. Okay. Sine 1 over x function, and you multiply it by x squared. So you multiply it by x squared, and it becomes like this. Oops. Right? It goes crazy inside here. So that's sort of what it looks like. Okay. Okay. So this guy, and then you define it to be 0 at 0 because it's not defined there, right? But if you squeeze it like this, then doing that gives you a function that's differentiable at the origin. Give you a function that's differentiable at 0. Okay. So this guy is differentiable, but the derivative is not continuous. F prime is not continuous at the origin. Right? F prime is not continuous at the origin. You see what happens. It's going to be oscillating, right? F prime is going to be going positive and negative and positive and negative. You know, F prime is going to be oscillating quite considerably there. Right, and it's not going to be continuous at the origin. Right, the derivative at the origin is going to be 0, but as you get closer to it, the derivative is going to oscillate wildly. Okay, so you get a discontinuity at the origin. Okay, so derivatives need not be continuous. However, they always possess an intermediate value property. Okay, and this will be pretty simple to prove. So here's the theorem. You have some function on some closed interval a, b, and it's differentiable on that interval a, b. So if the derivative at A is less than the derivative at B, then for every lambda in that interval, f prime A, f prime B, there exists a point between A and B where the derivative reaches that value. Okay. So it possesses this intermediate value property. If you have 2 points where the derivatives are 0 and 1, then whatever value you choose between 0 and 1, there's some place where the derivative attains that value. Yes, Leah?
Why do we have an open interval for x lying in the open interval of A? In the last row.
Because, so think here's A and here is B. F prime A, F prime B. Okay, so we're looking at the derivative of the function. Okay. What we're saying is that if you attain this value and you attain this value, then for every value between them, you're gonna hit it between A and B. Okay. So this is the way that it makes sense to phrase it this way. Okay. So the derivative has this intermediate value property, and the proof of it is pretty straightforward. So proof: consider the function g of t being f of t minus lambda t. Right? So choose your lambda, right? Choose your lambda between f prime of b and f prime of a. Right? And consider this function, just your function minus this line at that slope. It suffices to show that G prime equals 0 somewhere, right? Equals 0 somewhere in AB. Okay, and okay, and so what we're going to do is use the we're going to use Fermat's theorem, actually. We use Fermat's theorem. So we could have done this earlier. Okay. So it suffices to show that G attains a minimum at some x in AB. Okay? Because then by Fermat's theorem, we know that the derivative has to be 0 at that minimum. Okay? Okay, so let's do it. We say, well, G prime of A is going to be F prime of A minus lambda. Right? F prime of A minus lambda. Right? Well, lambda is bigger than F prime of A. Right? So this is negative. Right? G prime of B is F prime of B minus lambda. That's going to be positive. So if we're looking at the function g, right, if we're looking at the function g, at a and b, we know that the slope here is positive, right? We know that the slope here is positive, and we know the slope here is negative. Okay. Slope here is positive, and slope here is negative. So using what we said earlier, you can say, well, look, I know that the slope here is positive, so I'm going to take a line of slope half that of slope half of that slope. Yes.
Isn't that slope at B also positive? Yeah. Like in the
yeah. Sorry. This is the slope here should be negative, and the slope here should be positive.
Wait,
The positive should be.
This is negative.
This slope at B and
this is positive.
Yeah.
It's not limit, it's
Thanks. Next. Okay, so now it's ready. So what are we going to say? I say, well, look, I know that the slope here is negative, so I can't. So I'm gonna trap it between. I'm gonna trap it under a line. I'm gonna trap it under a line that has half of that slope. Okay. I'm gonna trap it under a line that has half of that slope. Half of that slope is still a negative slope, right? So what does that tell me? That tells me that in some neighborhood here, my function is decreasing, right? Because I'm under a line of negative slope. Right? I'm under a line of negative slope, so I can't have a minimum here. Over here, I'm going to trap it under a line. I'm going to trap it over a line of half of this guy's slope, right? A line with positive slope. So I'm over a line with positive slope. So I must be increasing this way, and so this could not be a minimum. Okay. So the minimums cannot occur at the endpoints. Okay. So. Okay, so what does it tell me? So that's the idea. I've written it more. Let me write it out. Let me write it out just to be careful. So think. So minima cannot occur at endpoints. Minima cannot occur at endpoints. For example, at A, G prime A is less than 0, that tells me that the limit of g of t minus g of a over t minus a is this number that's less than 0 as t approaches a from the right-hand side. Okay. Okay. So what is that? So this limit is equal to that number, which is less than 0. So I know that there exists a neighborhood, a plus delta, in which g of t minus g of a over t minus a is less than g prime over 2. Okay, let me draw the picture. Right, this thing here is 0. Here is g prime of a. Right, here is 0. Here's g prime of a. I know that the limit of this thing is g prime of a. So I know there's some limit. I know there's some neighborhood in which I'm trapped between in this plus half and minus half neighborhood, right? So I take epsilon to be 1/2 g prime a, right? I know that there's some neighborhood in which this thing is trapped between these two bounds, right? But that means that it's smaller than 1/2 g prime a, right? The upper guy, right? Epsilon is 1/2 g prime a. The upper guy is 1/2 g prime a. The lower guy is 3/2 g prime a. Right.
Is that do we take the limit of gt minus g over t minus a, or is it just?
Yeah. Right, we're taking the limit of this thing is g prime of a. So I know that I can trap it under half of g prime of a.
That's negative, right? Half.
Yeah. Yeah. This is a negative number. G prime of a is negative. Okay. Okay. So what does that tell me? That tells me that g of t minus g of a is less than sorry, let me So hold on a second. let me get my head straight. Right, of course. So g of t minus g of a is less than 0, right? Sorry, right? Because this number is negative and this number is positive. So multiplying both sides by t minus a, we get something negative. So we get g prime a over 2 t minus a is less than 0. Okay. Right. Right. In other words, g of t, right? G of t is going to be smaller than g of a. Right. So in that neighborhood, whatever you have is going to be smaller than that. So this couldn't have been a minimum. Right. So g of a is not the minimum. Okay. And then on the other side, you should do the same thing. G of b is also not the minimum. Right? Neither is g of b. So the minimum must occur. Minimum occurs in AB. Right? And so we're done. Okay, so that gives us this intermediate value property for derivatives. Okay. So as a corollary, derivatives cannot have any simple discontinuities. Right? Simple discontinuity, remember, meant that the limit existed from both sides. Right? So if the limit from the left-hand side equals, no, sorry, is less than the limit from the right-hand side, right? So suppose you have something like this. Here is x, and you're looking at f prime, and you find out that the limit from the left-hand side is less than the limit from the right-hand side. Okay. Okay. But you're supposed to have the property that you can get every value in between, right? So that's impossible, right? This is not going to have the intermediate value property, right? It's got this big jump, right? Okay. Similarly, if the limit from the left-hand side equaled the limit from the right-hand side, but your derivative there was different, right? If you had something like this, again, you're going to have you're not going to satisfy the intermediate value property, right? If the limit from the right and the limit from the left exist, but your function's value is up here, well, again, you don't satisfy the intermediate value property. Yes.
For proving the minimum cannot occur at the endpoint, how do we know g prime of a is less than 0?
Because we chose lambda to be bigger than g prime of a, right? Lambda was between g prime of a and g prime of b, right? So so g prime of a minus lambda is going to be negative, and g prime of does that make sense?
Okay.
Right. Lambda was bigger than g prime of a.
Okay.
Okay. So we've got 6 minutes left. Maybe we can do L'Hopital. I think at least we can do part of L'Hopital. Okay. So here's the statement. F and G are differentiable on some interval a, b, and A and B are allowed to be, A could be negative infinity, B could be positive infinity. Okay, so they're allowed to be finite or infinite. Suppose you know that g prime of x is non-zero on that interval, and suppose you know that the limit of f prime over g prime is a as x approaches some as x approaches a. Okay. And a is allowed to be finite or infinite. Right? A can be finite or infinite. Okay. Then if so there are two scenarios. If the limit of a And the limit of f and the limit of g as x approaches a are both 0, or the limit of g goes to infinity, is plus or minus infinity. Then the limit of the quotient of f and g as x approaches a is the same as the limit of the quotient of the derivatives. Okay, and this will be a consequence of the generalized mean value theorem.
Professor?
Yes.
Those are derivatives, right?
No, the limit of the quotient of the function will equal the limit of the quotient of the derivatives.
Okay.
This a is the limit of the quotient of the derivatives. If you prefer, we could just move this over there. Right? The limit of the quotient of the functions is the limit of the quotient of the derivatives, as long as that limit exists. Okay, so let's prove it, or as much of it as we can in 4 minutes. So let's, for simplicity, let's do the case where a is finite. Say a is finite. Let's assume a is finite. And we'll use the generalized mean value theorem in both cases. So, okay, so first off, say, fix epsilon greater than 0. Since the limit of the quotients of the derivatives equals a, we know there exists a neighborhood such that if we're in that neighborhood, a plus delta, then f prime c over g prime c minus a is small. So here is a, right? Here is the limit of the quotients, right? F prime x over g prime x, right? And what we're saying is that we can find a neighborhood, a plus delta, in which we're close to a, in which this quotient of the derivatives is close to a. Okay. There's a place where the quotient of the derivatives is close to a. Okay. So now we use the generalized mean value theorem. Now, take the interval x, y living inside of that neighborhood, a plus delta. Okay. So we take a x, y inside of that neighborhood. X, y living inside there. Okay. What does that give you? By the generalized mean value theorem, we know there exists a point C, right? There exists a point C in xy where the f of y minus f of x over y minus x equals f prime c over g prime c. Right? That's what the generalized mean value theorem gives you. Right? 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 Remember the generalized mean value theorem says take any 2 points. There's got to be some point where the ratio of the instantaneous velocities equals the ratio of the average velocities. Okay, so we're just using that. Okay, but this c is in xy, which is inside of a plus delta, right? So we know that this thing, right, is in the half epsilon neighborhood of a, right? It's close to a. Okay. Right? So that tells me that this thing is close to a. Right? This quotient is close to a. Okay. So let's do the first case. Sorry, I'm just take another minute, less than that I hope. Let's do the first case where the limit of f of x as x approaches a is 0, and the limit of g of x as x approaches a is also 0. Okay, so now let x go to 0. X go to, sure, no. Now let x go to a from the right-hand side. Okay, right, so we take the limit of f of x minus f of y minus f of x over y minus x as x approaches a from the right-hand side, right? Well, that's going to be what am I writing? This is wrong? Okay. Yeah. Sorry. No wonder you guys look confused. Yeah. Thank you. Those of you who are giving me weird looks the last 3 minutes. Okay, by the generalized mean value theorem. I said it, didn't write it. Okay. So this is going to be f of y over g of y. Right? Because as x goes to a from the right-hand side, f and g go to 0. Right? F and g go to 0, and so we get right. But as x goes to a, this thing always stays in the epsilon over 2 neighborhood of a, right? So that tells you that this thing stays within the epsilon over 2 neighborhood of a, and maybe we have to close it. Okay, because when you take the limit, you might end up tending towards the boundary. Okay, so we might have to close it. But in any case, this is all right. Okay, so we get this. Right. So that says that thus for all y in that a plus delta, we have that f of y over g of y minus a is smaller than epsilon, right? Because it's within the closed epsilon over 2 neighborhood. It's in the closed epsilon over 2 neighborhood, so it's certainly within the epsilon neighborhood. Okay. So what does it tell us? That tells us that whatever epsilon we choose, we can find a neighborhood of a in which f of y over g of y is close to a, right? So that tells us that thus the limit as y goes to a of f of y over g of y is a, right? The quotient of the derivatives. Okay, that's it. Sorry to hold you over.